I got a comment or two recently asking when I'm going to finish the Electronic Leadscrew project. And while I'm not entirely sure what that word means, I did just release a new version of the firmware that improves reliability and adds some of the features that you've been asking for. Welcome back to Cloud 42. I'm James. Well, if you've been around the channel for a while, you are no doubt familiar with my Electronic Leadscrew project. And if you haven't been and you just heard about me elsewhere on the internet, no doubt it's because of the Electronic Leadscrew project. If you're not familiar with it, the Electronic Leadscrew replaces the change gears on a manual lathe with an electronic controller and a motor, so you can change feeds and thread pitches by pressing buttons instead of messing around with gears. Now, since the project went live about 18 months ago, nearly 1,000 of you have started working on your own, and those are just the ones I know about. Since the project's 100% open source, there very well could be more than that. Well, today I'm announcing a new version of the firmware that addresses issues and adds some of the features that you've been requesting. We'll take a look at the features first, and then we'll take a look at some troubleshooting tips that might be helpful if you want to build one of your own. Incidentally, if you've been waiting for the control panel kits to be back in stock and you asked me to let you know, I'm letting you know. They are now back in stock. There's a link down in the video description if you're interested in picking one up. And I also have the interface PC boards in stock, and there's a link for that down in the description as well. Now let's talk about the features in the new version of the firmware. So I'll power this on, and you can see the firmware I have loaded here is version 1.3.01. And let's talk about what's in this. The first and most important thing is some reliability improvements in the firmware. There have been a few people that have struggled with electrical noise in their setup, which is, not that unexpected. You've got low power, low voltage microcontrollers running and serial communication in an environment where you've got high power stepper and servo motors, and of course the motor and VFD that are running the lathe, and using good grounding techniques, good cabling, routing, so that you're not crossing over the high voltage cables with the low voltage cables, using shielded cable, keeping the grounds of your motor and logic system separate. All of these things can help eliminate that. And in fact, I'm not actually having any noise issues in my setup at all. There are some people that are, so I have, in addition to providing a bunch of information on best practices for cabling, there are some changes in this firmware to try to make it more immune to noise. First thing I did is I slowed down the serial bus. The communication between the microcontroller and the control panel was running at 250 kilobits per second. I've slowed that down now to just under 100 kilobits per second, which makes the bits longer in time and will help to overcome long rise times due to cable capacitance from extra shielding and electrical noise that may be occurring in the system. And then, in addition to slowing it down to make the actual communication more reliable, I've added aggressive validation to try to detect and ignore any communication problems that do occur in the system. So the first thing I did is I made it so that it will validate that only one button at a time is being pressed. There are certain scenarios where a communication can be missed and the microcontroller will read back all ones and think that all of the buttons are pressed. And the code will now ignore that. If there's more than one button pressed, it just will ignore it. So if I'm pressing and holding one button and press any of the other buttons, it just completely ignores those until I let go and it reads no buttons pressed, and then I press something again after that, it'll then recognize it. So that prevents a whole series of problems that people were seeing where they'd be running, you'd get a bad read, it would think all the buttons were pressed and all the modes would change, which if you're in the middle of a cut is bad. So that should be impossible now. There are some other scenarios where a single bit error could lead to a button press detection. So I have modified it so that it has to read the same value back from the button array 3 times in a row. It's reading about 50 times per second, and if it doesn't get the same value 3 times in a row, it just ignores it. Now for the user, reading 50 times a second and using our meat fingers to press the buttons, you're not even going to notice that delay, but it eliminates another whole class of erroneous button reads that, again, I haven't been experiencing, some other people have. Now, this firmware, several people who've had problems have tried the new firmware and have reported that it's completely solved those issues. So best practice is to eliminate the electrical problems as best you can, and it is possible in most setups, but the additional validation on top of that to prevent problems if you do have electrical noise issues, I think is a worthwhile investment and probably should have been in the firmware from the beginning. Okay, the other thing on the validation front is I have also set it up so that many of the buttons lock while the lathe is in motion. So if I start this up, you'll see that the inch, millimeter, feed thread, forward, reverse, and power, all the other buttons are completely ignored. You can still change the feed rate while the lathe is in motion, because that's very handy, even in the middle of a cut, to change the feed rate to try to tune your chip formation. But the other buttons, like suddenly reversing it in the middle of a cut, that doesn't work now. And then once it's stopped, you can do it. You have to wait for it to completely stop. It's actually reading the RPM, and until the RPM is 0, it ignores all the mode changes. Now, if you really don't want the plus and minus buttons to work while the lathe is running, there's an option in the configuration file you can change, and it will lock those buttons as well. Okay, next feature is I've added support for the power button. Many people have been asking for this. Some people have submitted code changes to support it. When you press the power button, it powers down the display. The only thing that it leaves active is the RPM. So if you run the lathe with it powered off, you still get the tachometer, which is useful, but as you can see, the servo is not running, and in fact, it's de-energized, so the lead screw and the feed mechanism is all just free to turn on its own. Power this back on, and now this is locked and runs again. So technically, the code is still running. It's still generating pulses for the stepper or the servo driver, but it is turning off the enable line, so the stepper or servo driver is disabled. If you power it off and yours is still running, it's because you don't have your enable line configured or wired up correctly. Next thing is the tachometer stabilization. I'll go ahead and turn this off. Several people have reported that they didn't like how fast the tachometer was updating, so I modified it and configured it so now it only updates twice per second instead of 10 times per second, and it averages the speed over that half-second time, and so the display is much more stable. So here we go, 430 is kind of going between 430, 431, just based on quantization error. And that's much better than it flickering so fast you can barely even tell what it says. Now, if you want it to go faster or slower, that's also configured in the configuration.h file, and that can be tuned. Another feature that's been requested a lot is separate feeds for threading versus feeding. Many lathes don't have a single lead screw. They actually have two shafts. One lead screw for threading with the half nuts, and one shaft to drive the rack gearing for feeding. And often they're at different ratios. And so now if you go into the configuration.h file, you can configure a different ratio for feeding than you have for threading. And you'll need to figure out what you have to do on your lathe to switch, but if you switch from feed to thread or thread to feed, then you need to throw the feed or thread lever as appropriate on your lathe, and I'll leave that to you. Every lathe is a little bit different. And then the last thing that's in the firmware is a fix for large metric threads. There was an issue where a 32-bit register was overflowing for certain lathes with certain pitch lead screws, metric lead screws, cutting certain large metric threads. If this was affecting you, then as you went up through the metric threads, you get up to a certain size, and then the pitches were just wrong with no kind of discernible pattern. That's fixed. That fix, again, was suggested by a user, and I just increased the size of that register to 64 bits, and that solved the problem. I think that's all the new features in the firmware. Forgive me if I forgot anything. Let's go over to the bench now and talk about cabling. I get a lot of questions about what kind of cable to use for the electronic lead screw for wiring up everything from the encoder to the control panel. And you have kind of a couple of commonly available options. What I've actually used on my lathe is Cat5 cable, or Cat5e or Cat6. And this cable in this case is unshielded, though there are shielded variants. And the cable consists of 4 pairs of wires. So like here's the orange, there's an orange pair. Let me get this so you can see it. There's an orange pair, a brown pair, a green pair, and a blue pair typically. And each pair is just 2 wires. So if we look at the blue pair, there's a white wire with a blue stripe, and there's a blue wire, and they are twisted together. And when I wire up my control panel, for example, there are 5 wires. There's power, ground, and then 3 signals. And what I did is I just picked a pair for power and used the solid wire for the +5 and the white wire for the ground. And then I used 1 pair for each of the other signals. So each one I put the signal on the solid wire, and then I connected the white wire to ground. So every signal that's going through is on a twisted pair that has a ground wire twisted up with it, and that provides some measure of noise immunity in the system. And for me, on my setup, that's been plenty. If the Cat5 cable isn't working, and oh, by the way, this comes in stranded and solid conductor variants, I'd highly recommend using the stranded variants if you're using it on a machine where there's going to be vibration. The cable will last longer without breaking. Another option is shielded cable. Now this cable has a full foil shield, and no, I don't know what this stuff is. This is just some stuff that I had in a scrap bin that I probably got out of a dumpster at one point. But it's got a number of stranded conductors. They're wrapped in a foil shield, and then there's a ground wire, sometimes also called a drain wire. And so the drain wire is not to be used for a signal. It's used just as a shielding ground. So you connect the drain wire to a chassis ground or an earth ground on one end only, and it's not connected to the ground for the signals. And then you use the wires inside the foil shield for your power and your signals. This stuff works pretty well, and it is better at electrical shielding than the Cat5 cable. But the downside is this cable has more capacitance because every wire is inside this grounded shield. So it's like connecting a capacitor between the wire and the shield. And that can help with noise immunity because it filters out the high frequencies, but it can also cause problems with data transmission because it filters out the high frequencies. Let's take a look at how this works. So you've got some old setup sheets here, and let me just scribble something on here. Where's my pen? There we go. So if we look at how the wiring works, we have we have 2 devices. We have the microcontroller and the control panel. And we'll just simplify this. And you'll have a ground wire that connects those. So on each end, this is connected to ground. And then we'll look at just one of the signal wires. Now, the microcontroller is 3.3 volts. And the control panel is 5 volts. So there is a voltage translation circuit here. We'll just go ahead and ignore that for the moment. And the wire goes through that voltage translation and connects to both ends. Now, what's really going on in here, because these are different voltages and we need a bidirectional bus, you can't have both ends driving voltage into the system. So what's actually happening is there's just a transistor in here that can pull this down only, and you have that on both ends. And that's terrible looking. And so in order to allow to send a high signal, there is a resistor connected that's a part of the voltage translation circuitry on each end. There's a 10K resistor that pulls that line up positive. And if the microcontroller wants to send to 0, it turns on this transistor and it pulls that line down. Same thing if the control panel on the other end wants to send to 0, it turns on this transistor, pulls this line down to ground to indicate a 0, or it releases it and allows the resistor to pull it up high for a 1. Now, the issue is if you're using, especially if you're using shielded cable, but if you have any significant length of cable, every cable has some amount of capacitance, and that will show up as a capacitor. It will look to the circuit like a capacitor between the signal line and the ground. So you have a relatively high resistance. In this case, it's a 10K ohm resistor pulling the line high, but you have a capacitor that has to be charged in order for that to go up. So instead of having a nice, clean 0 to 1 transition on your signal, you end up with a taking the high frequency edge off of that, and you get a slow rise time. So if you have a clock that's clocking that pulse, it goes low, so your control panel knows it needs to send a 1, so it releases the line, expecting it to go high so that when this clock goes up, it reads at a 1. Well, if it goes up too slowly, it may not be high enough to read as a 1 yet. So the more capacitance you have in the cable, the more it slows down these edges, and the more you could start to run into problems with the microcontroller communication. Now, if that's what's happening to you, you will most likely see it as the control panel just going crazy. It won't be stable, stuff will just be flitting all over it because the signals that are being sent down are being universally slowed down. The 1 bits, at least the initial 1 bits, aren't being registered correctly, and you'll see the thing going crazy. If it's stable, you're probably not seeing this particular issue. Now, even if you used to be seeing this issue, updating to the latest firmware can help because I slowed down the baud rate of these signals from 250 kilobits to less than 100 kilobits, which allows more time on the clock pulse for this to come up so it can withstand more capacitance on the line. The astute among you may say, well, maybe you could just reduce the value of those resistors. And technically, yes, you could. That would decrease the rise time and put some of these edges back. The problem is that the microcontroller output is only able to sink a certain amount of current. It's about 4 milliamps, so if you put a few low resistance pull-ups in here, it'll start to have trouble pulling the line low. If you've purchased one of these interface PC boards for the electronic lead screw, you know that the servo or stepper motor is connected with these screw terminals. And what this is just a 2-piece connector. One part is soldered to the board, the other part with the screw terminals plugs in, and then there are screws and openings where you can put in the wires to clamp them in place. And a couple of people have run into problems with this connector. Now if I tip this up, you can see down into the openings for the wires, and you can see that there's a bar there for clamping the wire in place. And it is clamped all the way closed the way it comes from the factory. And if you turn counterclockwise to open it, you'll see that bar drops down, and then you can stick the wire in below it, and then turn clockwise to raise that bar and clamp the wire in place. And that's the correct way to connect a wire to one of these terminals. I didn't strip this wire, so yeah, it's not making contact, but this is just for illustration purposes. What a few people have done is they didn't realize that this connector is actually closed from the factory, and they actually inserted the wire below the clamp and then turned counterclockwise to pinch the wire down against the bottom of the connector. Now this will sort of, in some circumstances, now see I just backed the screw out, but under some circumstances you can actually get it to clamp down so that the wire seems like it's physically secured in place, but it will not make electrical contact in that position. To make electrical contact, you need to back out the screw to lower that bar, then stick the wire in above it, and then turn clockwise to clamp the wire up against the screw terminal, and that will make good electrical contact. If you do it the other way, you might get away with it, you might not. It might be intermittent, and those are the most confusing kinds of errors. So yeah, counterclockwise to open, put in the wire, clockwise to lock it in place. I've also spoken with a few people that have struggled with soldering on these little boards, and you know, it's not that surprising. There are a lot of little connections on here, right? The connectors on the bottom are not on there. You have to solder those, and they've got 20 connections each, and then you've got the 5 pins for the display connector and the 6 pins for the servo connector plus the power. Now, if you have a problem getting the power connected, those are nice big pins. It's pretty easy to see, pretty easy to solve those issues. But if you just have one of these logic wires that's messed up, or if you end up lifting a pad on a connector, that can be pretty difficult to troubleshoot if you don't actually have the schematics and you don't understand everything that's going on the board. So I went ahead and went through, and on the documentation wiki there will be a link down in the video description to the GitHub page, and then the documentation is linked up there. I put together some images that show where you can test the solder connections on the board. And I've got them printed out here, comic size. But the way this works is, so I've got the DIO pin, the last pin over here, that's soldered down on the board, and there are traces that come over, and there's a lead on the top of this transistor Q3 that it should be connected to. If you had a problem with that solder joint, you can detect that by checking for continuity between that pin and this pin on this transistor. So if you just can't get something to work, you can get a multimeter, set it in continuity mode, and you can test some of these connections. So I've got my EEV Blog Bryman BM235 here, and I will just set this to continuity mode. And now if I touch the leads together, it beeps and flashes. So then I can look at my comically large image up here. I can see that DIO should be connected to this pin down here on Q3. So I touch one to there and touch the pin on Q3, and I can see that I have continuity. Next pin over should be connected to Q2. I can check that. Next pin over should be connected to Q1. And I have good continuity there. So I can then just go through all the diagrams here, and I can check the continuity for all of these pins. And yes, these are small, and yes, you may need magnification, but this at least gives you a way, without an oscilloscope or without complex equipment, to troubleshoot what's going on. Unless you drive this thing with reverse polarity or too high of a voltage or have a massive static discharge, the electronics on these boards are actually pretty robust. So if they're just not working and you're suspecting a problem with the board, checking the continuity can find lots of the kinds of issues that you're likely to run into. One thing to note, if you're testing like continuity from these pins, I know from my diagram over here that pin 0 should go to the side of this resistor R7. So the best way to do that is to actually touch the top of the pin, not down in the solder, because the solder is probably going to be connected, but if I have a problem, the pin won't be. So I'll touch just the top of the pin and then actually touch the resistor, and I can see that I have good continuity from the metal of the pin itself down to the resistor. Now for extra credit, if all of that checks out and you're still having problems, you can actually test your cables end to end by connecting them. There's another diagram in here showing the display board and where all the signals should terminate, like the STB, clock, and DIO. So here's the DIO, should be on the top of this resistor. You can blow these up on the website and see them much better. So DIO should connect to there, and I know from this other diagram, the DIO should be on the tip of Q3. So I should be able to check from that resistor on this other board to the pin on Q3, and I can see I have continuity through there. So I know that not only are my solder joints good, but my cable is good and it's wired correctly. So most people are not going to need to get down to this level, but if you're having trouble and you know, are not certain of your soldering skills or certain of the soldering job on the board, these diagrams will give you another tool to help troubleshoot it and maybe solve a problem for somebody. At least that's the hope. I hope this was helpful. If you are interested in building your own electronic lead screw, I have both the control panel kits and the interface PC boards back in stock, and there are links down in the video description. If you're enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching. Okay, I'm going to call that good. Need to find my remote and stop, and stop.